Okay, we were discussing about the architecture of 8085 microprocessor. So we have discussed almost all the blocks in this diagram except few signals that we will discuss, and then I will come to the pin diagram. Okay, so you've seen that these resistors, we have 6 general purpose resistors, that is B, C, D, E, H and L. So they are 8-bit resistors which are given to the programmer. So the programmer can use them to store the data, to move the data, to perform various arithmetic and logic operations during the execution of the program. Okay, so then when we have two 16-bit registers, program counter and stack pointer. So program counter holds the address of the memory location from which you are going to fetch the next byte. Okay, so that similarly stack pointer is also used to hold the 16-bit address of the memory location, which is called as stack. Okay, so that we have discussed. And then what happens basically when the processor starts executing an instruction, so it loads the program counter with the starting address of the memory location, right? So the contents of the program counter, they are then uploaded on your address bus, and the address bus is divided into two parts, lower 8 bits and higher 8 bits. Okay, so higher 8 bits, they are used for address only, but the lower 8 bits, they are used to carry the data as well as the address, right? So that lower 8 bits, they are latched basically using a specific pin on the processor, which is called as address latch enable. Okay, so it is active high pin. So the processor sets the signal from 0 to 1. So when it goes from 0 to 1, your lower 8-bit address is latched, and in the next part, now these 8 bits or 8 lines, they can be used to carry the data. Okay, so how an instruction is executed. So the PC loads the address of that memory location is loaded in the PC, which is placed on the address bus in the higher and lower parts. Okay, so your memory location gets identified. Okay, then you have the memory read operation. So there is a read signal which gets activated, or the processor basically activates this read signal, which is a logic or low level signal. So it goes from 1 to 0, and your memory chip gets enabled. So whatever the data on that at that particular location, so that is placed on the data bus. Okay, it is placed on, in fact, the address bus, and from the address bus it goes inside the instruction register. So the instruction register, which holds the 8-bit opcode, it gives it to the instruction decoder. So this instruction decoder will decode the instruction. Okay, and then it gives certain instructions to the timing and the control circuit. So this timing and the control circuit will generate various control signals, okay, which are used to activate the various logic circuits inside the processor, and that instruction is executed. This is how it is done. Okay, this is what we have discussed. So we have discussed that we have a register A accumulator, which is a 8-bit register, and it is basically part of ALU. So that is why it is separate from these. Okay, so because all the arithmetic and logic operations, they are performed with A as one operand. So one operand to ALU, it is fixed. The second operand, it can come from anywhere. It can be a register, that is general purpose register B, C, D, H, L. It can be immediate 8-bit data. It can be some data from the memory. So whatever data comes, the second operand, it first goes with the temporary register. So from the temporary register, it is combined with the accumulator depending upon the instruction, and your ALU generates a result, which is again basically stored back into the accumulator. Okay, and depending upon this results in the ALU, the flags, they are affected. So we have 5 flags that we discussed: sign, zero, carry, parity, and auxiliary carry. Right, similarly there is one block for interrupt control. So interrupts, we have 5 interrupts here. INTR has the lowest priority and trap has the highest priority. So I will discuss about this, of course, in more detail when we will discuss interrupts. Okay, so the interrupts are basically used to interrupt the processor. Okay, if some other device that wants to use the processor for doing some other task, so it can send the interrupt signal to the processor. So the processor will execute the current instruction, and it is up to the processor whether to respond to that interrupt or not. So that is given by interrupt acknowledge. Okay, So interrupt acknowledge int, which is a logic low signal. So it is a generated by the processor to that device that okay, it is ready to process whatever is the request from that device. Okay, so all of these are interrupts. So they have different priorities. Some are maskable, some your trap is non-maskable. It means you cannot mask this interrupt. Okay. Otherwise, you have some software instructions in which you can enable and disable the rest of the interrupts. Okay, so that will come to this. Then we have come to the serial communication. So we have two pins for serial input data and serial output data. Okay, so that we discussed what is the meaning of serial communication. You want to transmit, you are transmitting one bit at a time, right? That is what is serial communication. And then there are some more signals which we have to discuss now. So power supply, of course, it operates on 5-volt power supply and ground. So we have two special pins on the processor for this purpose. Okay, X1 and X2, these two pins, they are used to provide a crystal oscillator to the processor. Okay, so most of the processors, 8085 processor, it operates at a frequency of 3 megahertz clock frequency. Okay, but it's the internal divide by 2 circuit. So the oscillator that you connect, it must have a frequency of 6 megahertz. Okay, so that it gets divided by 2, and the clock signal that is generated, it is operating at 3 megahertz frequency. And then there is another signal which is clock out in the microprocessor. Okay, so clock out pin, it is basically used to generate a clock signal. Okay, or it generates a clock signal because see, when you are using a processor, so you have many other components with that, many other components are interfaced. Okay, so there may be requirement that for other components they may require a clock signal to operate, because all the digital circuits that they are operated using the clock signals. Okay, if they are synchronous, if it is synchronous circuit, so you can use this pin clock out to provide a clock signal to the another chips or another circuits in the system. This is what is the purpose of clock out. Okay, and of course write and read that. So if the processor wants to do a write operation, it means if you want to store some data into the memory, it will activate write. If it wants to read some data from the memory, it will activate read. Then these two signals S0 and S1, which are called the status signals, they are rarely used. Okay, and in fact they provide the status of the processor. Okay, like when the processor how the processor operates, it operates in a sequence: fetch, decode, and execute. Okay, so these two pins S0 and S1, they give the status whether it is a that at which point is basically the processor, it is a fetching instruction or it is a decoding or executing instruction. Okay, or even they are used if you see, when we see the timing diagrams. So for opcode fetch, they have some values. For memory read, for memory write, they have different values. Okay, so they are generated, they are basically again controlled or set by the processor to check the status whether it is a opcode fetch is going on, whether memory read is going on, or whether memory write is going on, and so on. Okay, and then we have reset pin, reset in. This is again a active low pin, logic 0 pin. It means if you apply a high to low pulse on this pin, the microprocessor, your processor is reset. Okay, so what do you mean by reset? Resetting any system, it means it will start from the starting point. Okay, so whenever this pin is activated, so this is basically given by some device external to the processor. Okay, which wants to reset the processor. So when you reset the processor, the program counter is basically reset. It goes to the starting memory location 0000H. It means the execution of the programs will now start from starting address. This is what is the meaning of resetting. Okay, so whenever they reset the microprocessor, all the operations, they are suspended. Whatever the processor it is doing, it will stop. Okay, and its program counter will be loaded with the starting memory address, that is 000H, right? And similarly, you have a output pin which is reset out. So just like we have said that okay, we have two pins for connecting the crystal oscillator to the processor, and one pin clock out, which may be used to provide clock signals to other devices in this system. Similarly, so you have a pin for reset. You can reset the microprocessor by applying a high to low pulse on this pin. The processor will suspend all the operations and its program counter will be loaded with the starting address. Okay, so it will start now executing the programs from this location basically once it is reset. So this reset out can also be used, which is active high pin. So by the time you are resetting this processor, so there may be a need to reset some other devices also which are connected in the system. So this reset out can be used to reset other devices, okay, which are connected or interfaced to the processors. And then we have one more important signal here, IO/M bar. Okay, this is basically used to indicate whether the operation that the processor is doing, whether it is related to input output or it is related to a memory. Okay, like see, when you have microprocessor initiated operations, it can be memory read or memory write. Okay, the processor can read the data from memory or it can write the data into the memory. Similarly, the processor can read the data from the input or it can write some data to the output device. So that is basically given, the status of that is given by this signal or this pin. So as you can see, if it is 0, it means it is a memory related operation. If it is 1, so it is a input output operation. Okay, so this pin is basically combined with read and write signals to generate 4 different signals, and just like, see how it is done. This is your processor 8085. Okay, so you have 3 pins on this. One is for read, one is write, one is to show the status whether this read or write operation is related to the memory or it is related to some input output device. Okay, so this input output, if it is 1, it means input output operation is going on. If it is 0, it means it is a operation related to the memory. Okay, so it means it can be memory read or memory write. Okay, so what is basically done, we basically generate 4 different control signals, one for memory read, one for memory write, one for input output read, one for input output write, by combining these 3 signals. Okay, so how that has to be done. Suppose you are reading some data from the memory. Okay, if it is a memory read operation, so you have a microprocessor and you have some memory and you want to read some data from the memory. Okay, so this is memory reads operation is going on. It means which 2 control signals will be used by the processor. One is of course the read. Another signal, this will be used IO/M bar. Now since it is a read operation, it means this signal should be 0, and it is a memory related operation, this should also be 0. Okay, so by combining this 0 and 0, you can generate a separate control signal which is specifically used for memory read only. Okay, because see, on the memory itself we have 2 pins now, one is for memory read, one is for memory write. Okay, it means what the processor has to do, it has, if it has to read some data from the memory, so this read signal must be activated. Okay, so you cannot now see this read signal, it cannot be directly connected to this because this read signal has to be connected to some input output device also. So how you can differentiate whether you are going to read the data from the memory or it is going to be read from the input device. So for that we have one more pin here, IO/M bar. So it has to be 0 or 1. If it is 0, it is a memory operation. If it is 1, it is a output operation. So to avoid this confusion, what we do, so if this signal is 0 and read is 0, it means you can say, okay, definitely it is a memory read operation. Okay, so you can combine these 2 signals using a logic circuit, very simple OR gate. Okay, so if you use a simple OR gate, So this will give a signal which is be used for memory read only. Active low signal, of course. Okay, because this is a OR gate. Of course, this is represented that in the digital circuits. Okay, it is written in the form of inverted NAND gates. Okay, so if this input is X, this is Y, Z. So what is Z in this case? It is X bar, Y bar, whole bar. Okay, because the input is already inverted, we have a put inverter here. So it is X plus Y, nothing else. Okay, this is just a notation that is used in the book. Otherwise, you can use a OR gate simply here also. No issue. Now see, when this is 0 and this is 0, it will get output will be 0. Okay, it means now this memory read will be permanently connected with the read signal of the memory chip basically. Okay, because anyhow if it goes to 1, it goes to 0, your output will be 1, it will not be activated. So at a time a particular control signal is activated depending upon the combinations of these inputs. Okay, similarly if it is a memory write operation, it means this pin must be 0 and now this write signal must also be 0. So you can combine again these two using an OR gate again. So this will provide a memory write signal. Okay, now this signal you can permanently tie this signal with this write pin of the memory chip. Similarly, you can generate two more signals for input and output read. So what is that in that case? Now this should be 1. If this pin is 1 and this is 0, then only it should generate a logic 0. So how you can do that? It means if it is 1, it has you can just simply invert it, put an inverter here and then combine with this using an OR gate. This will give you input output read signal, which is active low signal. Okay, now this will be at logic 0 only when this is 1 and this is 0. This is what we desired. Similarly, you can combine these two, input output and a write signal, to generate a input output write operation. Okay, and how it will be done? So you can again use this signal, invert it and combine this with this inverter, write signal using a OR gate. You will get input output write signal. Okay, so you have generated 4 different signals: separate signal for memory read, separate for memory write, separate for input output read, separate for input output write. Okay, so this you can now connect to the input of this read signal of the input device, and this can be connected to for write pin of the output device. Similarly, this for the write and the read pin of your memory chip. Okay, so you have generated enough separate control signals, right? Otherwise there might be a confusion. Okay, so coming back to this, so okay, this signal is clear IO oblique M bar, so it is used to indicate whether it is a memory operation or a read write operation. And then we have 2 more pins here. Sorry, two more pins are here for DMA, which is given here in the timing and the control circuit. This is direct memory access. Okay, HOLD, hold, and HLD. I think only these 2 pins are now left. The rest we have discussed all the pins. See, what is the meaning of these 2 pins, hold and HLD, or what is the meaning of this? Sorry. So here two pins, one is hold, another is HLDA, which is called as hold acknowledge. Okay, they are used for, they are basically used by DMA controllers. DMA stands for your direct memory access. Okay, what is the purpose of this direct memory access? See, your processor and the memory, they are interfaced. This is suppose your microprocessor, this is your memory. So they are interfaced with each other, are connected with each other using certain buses that you know. This is control bus, this is data bus, which is bidirectional in nature. This is address bus, unidirectional. Okay. So if any device, if any other device, input output device, if it wants to send some data, it has to go through the microprocessor. Okay, so there is no direct connection between the your input output device and this memory. Okay, so all the data transfer is controlled by the microprocessor. Okay, so what we do in the direct memory access, basically we bypass this microprocessor. Okay, so the data can be directly transferred between the memory and the device without this you can say by bypassing this microprocessor from the picture. Okay, and that is basically done by using these two pins, hold and hold acknowledge. Okay, so how it is done? So you have some device. Okay, so this device is connected to this memory, of course using the same buses that we are used for this processor database. Okay, and let us suppose it wants to transfer some data to the memory and it does not want to involve this microprocessor into the role. Okay, so what it does, it gives a signal to the microprocessor on this hold pin. Okay, so it is input basically. So this device will send a signal to the processor on the hold pin, which will indicate that okay, the process, this some output device is trying to transmit some data to the memory. Okay, or it maybe it want to read some data from the memory. Okay, so what the processor will do, whatever the instruction, wherever it is at that time, it will stop executing the program and it will send a hold acknowledge signal, which is output signal to that device. Okay, so this device will send hold signal to the processor. The processor will acknowledge this request by sending another signal, hold acknowledge. Okay, so once it transmits this hold acknowledge signal, so the processor will stop executing the instructions, and in fact its data and this address bus, it loses the control basically. Okay, so this is what the meaning of the hold. So when the hold signal is activated, the data and the address bus is released by the processor. It is not going to use it now. Okay, so that data bus is basically used by this device for data transfer. So it directly transfers the data from this device to the memory without using this microprocessor. So it is used for fast data transfer basically. Otherwise from this device it has to go to the processor, then from processor to the memory. Okay, so but if you want to have a direct data transfer between the memory and some input output device, so that device can send a hold request to the processor. The processor of course will acknowledge that request by sending acknowledge signal, which on the output pin hold acknowledge, and once it acknowledges that request, it loses the control of this address and the data bus. Okay, now that those buses, they are basically free to be used by another device. So this device will transfer the information directly to the memory using the same data bus, because now they are loosed by this processor, they are not being used. Okay, so once this data is transfer is complete, this will stop this hold signal, this device. Okay, so the processor will again resume the control of the address and the data bus and so on. Okay, this is what is called as direct memory access. Okay, and there is of course one more pin which is, I think I have not discussed, which is called as ready pin. Okay, So this ready pin is basically used to can say delay the processor if there are some slow peripheral devices which are connected with this. So it goes to into a wait state for some cycles, for some clock periods, right? So this is what is about this internal architecture. So this internal architecture is now mapped to the pin diagram. If you see the pin diagram of 8085, now you will be see this is the pin configuration. It is a 40 pin integrated circuit. 8085A or 8085. In fact, 8085 is the advanced version of 8085A. It includes all the instructions of 8085A plus two more additional instructions. Okay. Otherwise, the pin configuration is same for both the processors. So we see how what are the different pins available on this IC. So pin number 40 is your VCC, pin number 20 is your ground VSS. Okay, so this is plus 5 volt power supply at pin number 40. X1 and X2 they are used to connect external crystal oscillator. Okay, so rest of the pins that we already discussed, it is just a numbering now here. Okay, what is the purpose of each pin that you know now? Okay, reset output, serial output data, input data, trap, these are all interrupts. This is interrupt acknowledge signal. These are the lower 8-bit address which are used to carry data as well. Okay, similarly these are the higher 8-bit address, pin number 21 to pin number 28. S0 and S1 status signals. This is the read signal at pin number 32, write, ALE input output to public memory, ready, resetting, clock out, HLDA, hold, everything is we have discussed. Okay, so this is again the same diagram, but it is written in a represented in a different fashion in which the pins they are basically grouped together. Okay, like see, so A pin number 19, 12 to 19, this is the multiplexed address and data bus. Pin number 21 to 28, this is the higher order address bus. Okay, so 20 and 40 they are both related to the power supply, so they are represented at one point. X1 and X2 pin number 1 and 2, so oscillator is connected here. Okay, so these two pins, pin number 4 and 5, they're for serial communication. Pin number 6 to 10, all these they are externally initiated signals, which are basically the interrupts. Okay, so another device will provide another device basically generates these signals by giving some interrupt to this processor. Okay, so this we have discussed ready, hold, and resetting, and these are some acknowledgement. These two are acknowledgement signals: interrupt acknowledge and hold acknowledge. So whenever some other device it interrupts the processor, so whether to you can say process that interrupt request or not, so that is basically given as acknowledgement by the processor to that device through this signal interrupt acknowledge. Similarly for hold, it is this hold acknowledge. Okay, and then there are these signals, they are grouped into the control and status signals. Okay, so ALE, you know, address latch enable, which is used to latch this at lower 8-bit address. Status signals, input output memory, read and write, and we have seen that how you can generate 4 different control signals by combining these 3 signals. Okay, then 2 pins are there, one is for reset out and one is for clock out. If you want to use this microprocessor as a clock generator for some other device, or if you want to use it to reset some other device which is connected in the system, so you can use these 2 pins. Okay, so anyhow, you need not to, you can say you need not to remember the pins of this, what is which you can say function is located at which pin. Okay, so if someone asks you a question, okay, where is the trap, so you can say pin number 6, that is just nonsense. Okay, it is everything given in the pin diagram. Okay, so what you must remember or you must understand is what is the role of each of these pins. Okay, how they are basically used for the communication and the timings, that is important. Okay, not remembering the pin diagrams or the pin configurations. Okay, so next we will study the timing diagrams, how the microprocessor controls the communication between the memory and the processor is controlled by various control signals that we will discuss now. Okay.